Good evening, ladies and gentlemen. In this lesson, we're going to be continuing with the organic chemistry reactions. In the lesson that we did on Tuesday, we managed to get through all of the addition and substitution reactions as well as combustion. And in this lesson, I'm hoping to get through elimination, cracking, esterification, and a little bit on polymerization. You're going to find that I go into way less detail on polymerization than possibly your teacher did or than possibly the textbook does, but I promise you that the examples that we do are the ones that you're most likely to get asked, which I think is smart. I think we're going to study smarter rather than harder. So we're going to make sure that when we focus on things, we focus on what you're really going to get. All right, so without further ado, let's get going. All right, just getting all my screens set up in the right place. Okay, so what we're going to be looking at tonight is we're going to be looking at elimination reactions. Yeah, just checking my spelling. So elimination reactions. If you remember in the lesson on Tuesday, I specifically illustrated that with an addition reaction, we go from a double bond to a single bond. With a substitution, we usually go from a single bond to a single bond. And with an elimination, we go from a single bond to a double bond. So the key thing that you're going to find from an elimination reaction is that we're going to produce alkenes. We're going to produce things that have a double bond in them. Now, fortunately for elimination, it's a rather easy one if you understand that you can only do an elimination with two starting materials at a metric level. We either start with an alcohol or we start with a haloalkane. In both reactions, you're going to produce an alkene and various other products. Now, what we need to look at here is what you're going to add to each of these to get the different reactions. And this is where a lot of people get confused because they go, I know that I add something, but I get confused as to what I add where. So I'm going to explain to you how I remember it. I have a little picture in my head that says, when you react an alcohol to make an ester, you use sulfuric acid. So the back of my head goes, alcohols are linked very closely to sulfuric acid. So with my alcohol here, I'm going to make sure that I add sulfuric acid, and that is our acid. So with my haloalkane, what I'm going to do here is I'm going to add a base, and it's got to be a strong base, but more importantly than being a strong base, it must also be a concentrated strong base. So typically this would end up being sodium hydroxide, but specifically concentrated sodium hydroxide. So you also end up with a number of other products. With our alcohol, reacting it with sulfuric acid, please note, I think you can actually use phosphoric acid as well, H3PO4, so it's also an option. But my brain tells me sulfuric acid because I link the alcohol and the sulfuric acid like we'd have that reaction where you do your esterification. This isn't esterification, but my brain just says if I've got an alcohol, sulfuric acid is a logical thing to pair with it. Okay, when we produce our alkene, we are also going to end up producing over here water. And when we have our haloalkane reacting with our strong base, we also produce water and we produce a salt. Now, the identity of this salt is going to depend on what halogen we had as part of our haloalkane, as well as which of the group 1 metals you used in your base. So it's usually sodium, lithium, or potassium. So let's use an example. Let's say that my haloalkane has chlorine in it. Then I'm going to produce a salt that is Na. I'm going to try and color coordinate this a little bit, NaCl. But if instead I had used a halogen that had bromine in it and I'd used lithium hydroxide, then I'd get lithium bromide. Okay, so I hope that so far as an overview, this makes sense. Okay, we'll do a little bit of practicing. Please note something else. If you start with a haloalkane And instead of using a concentrated base, you instead use a dilute strong base. Then we actually end up doing our hydrolysis reaction, which is a substitution, and we end up producing an alcohol. So it's very important when we talk about reacting a haloalkane with a base that we're 100% certain if it's concentrated or dilute. They love picking on this particular reaction because they can quite often say a strong base and they don't tell you if it's concentrated or dilute, and then you need to know what your products are. Now, we had an exam question a few years ago which got super cheeky on this, because what you ended up doing, I'm just going to move this a little bit across, is I had two types of reactions, okay? So the one was a haloalkane with a strong concentrated base that gives me my alkene, water, and salt. If we'd done this instead with a dilute base, our products would be an alcohol and a hydrogen halide. Okay, by hydrogen halide, I mean if this had chlorine in it, then it would be HCl. If it had bromine in it, it would be HBr. Please note, as a rule, most of these substances are also relatively acidic. And the way that this question worked, which actually got really ridiculous, was that they said it produces X plus Y plus Z. And you had to tell single-handedly from the fact that there were 3 products and not 2, that the base had to be concentrated and that you had done the elimination. Very sneaky, but it's how they fitted everything in. Okay, so this is one of their big all-time favorite reactions, is a haloalkane reacting with a strong base, and depending on if it's concentrated or dilute, you get 2 different products. We're going to be talking tonight specifically about the elimination, but I had to mention, just to prepare you for the fact that it's where people get very confused, that you could just as easily, from a strong base, if it's dilute, end up with this reaction instead. Another way that they show the difference between concentrated and dilute is they may refer to this as NaOH aqueous, and this one as NaOH in ethanol. Okay, so one of the ways that they kind of show that there's lots of water, it's one that I've noticed it pops up every now and again, it actually confuses people, but if it's aqueous, you can assume that we got some water. Now, don't assume that aqueous always means dilute, but I've seen questions where instead of saying concentrated and dilute, they say one with sodium hydroxide and ethanol, and the other with aqueous sodium hydroxide. And that was how they indicated that there was a difference. So just so you know, this isn't guaranteed to be dilute, but if the other one's specified as being in ethanol or ethanolic, then you know that this is the more dilute version. All right. Now, this is quite a lot in a short space of time, so I'm hoping that you get all of the ideas here. I'm hoping to make this a little bit harder than last time's. The other thing here that we need to know about is when it comes to elimination reactions, just like with the addition reaction where we had to use Markovnikov to predict what our most populous product is, which is our major product. That means just more populous means we get more of it. So if I need to know which is the major product versus the minor product, I applied Markovnikov's rule. We're going to be working on Zaitsev's rule tonight. And Zaitsev's rule says, okay, so I'm just going to quickly write this in. Zaitsev, just if you look on the internet, I'm looking up how to spell it here, but this is one spelling of Zaitsev. I can promise you I looked on the internet and there are about 10 different versions of how to spell Zaitsev. I've seen it with a Z, I've seen it without a Z, I've seen it with V's instead of F's. In an exam, I think we go with phonetic spelling. If I look at what you've written and it looks like it says Zaitsev, you're getting your marks. Okay, so please don't panic if your teacher's written a different version. I'm going with the ones that I've got on my official notes, but I can promise you I've seen different spellings on the internet and in textbooks. So with Zaitsev's rule, here what we're going to be doing is, in both cases with the alcohol and the haloalkane, we're going to have a leaving group. The leaving group is either your OH, the hydroxyl group from your alcohol, or what I'm going to just call X from your haloalkane. Please note this X could be chlorine, fluorine, bromine, or iodine. That's going to be a good leaving group. So we're always going to start with 2 neighboring carbons, one of which has our leaving group, and there's a line there, and one of which has a hydrogen. You cannot actually get elimination if you do not have a carbon next to the leaving group that has a hydrogen. The double bond is going to form on one side, let's be nice here, on one side of this bond. So you've got to have one of these 2 carbons with a hydrogen will have elimination. Please note, if you don't have a carbon that's got a hydrogen, it can't be on that side. Sneaky. So what we look at here is, imagine that this has a methyl group and a methyl group, and this side has only hydrogens. Either way, this is going to leave. Leave as in be removed to form part of my water. Okay, there or there. What leaves with it, and this is where it gets a little bit unfair. If you remember with Markovnikov, I told you we put the hydrogen on the side that's already got more hydrogens, or the most hydrogens. Here, we're going to do the opposite. So before we enrich the side that was already enriched, here we're going to take away from the side that already doesn't have. So here, the hydrogen there will leave. So we remove the hydrogen from the side that's already got, which means that the double bond will form in that position when these 2 leave. So that is your rule, okay? You always look at your leaving group, which, as I said, will be the hydroxyl group or the halogen atom, okay? Technically a halide, I guess. You're going to look at where that is. I find I circle it, then I look for the hydrogens on either atom. Now, please note here something important. If I have 3 hydrogens here, they are all equivalent, and it doesn't actually matter which one gets removed. The double bond will be there, and this carbon will just have 2 hydrogens. All right, ladies and gentlemen, I'm going to quickly stop sharing so that I can just check how many of you I still have understanding what we've done. So can I double check, is everyone still with me? Yes? Does everybody understand that in an elimination, we form a double bond? If you start with an alcohol, then you're going to use sulfuric acid. If you start with a haloalkane, you're going to use concentrated sodium hydroxide. If you accidentally said you'd use dilute sodium hydroxide, it wouldn't be the elimination. You'd instead do a substitution reaction, which is where we turn a haloalkane into an alcohol, and that is called your hydrolysis reaction. Okay, so that's if things don't work the way they ideally should. Okay, now what we did in the lesson on Tuesday that I found that worked very well for most of you is we actually practiced one example on this, or 2 examples. So I've done something very deliberate right now, where I've actually taught you 2 things at the same time, because I want to be able to see if you remember what the different conditions are for the 2, because it's very easy if there's only one reaction to figure out how to replicate it. But if there are 2, you've got to think a little bit harder. All right, so let us get going. I'm going to quickly clear this of all of the information that we've got here, and then we're going to just start doing examples. So I'm going to start with my first example. There we go. Okay. Can anyone tell me, if I just fill in all of the hydrogens on here, what is the name of this compound? I'm going to do a little bit of extra practice in between while we're going. Anyone got a name?
No, is it butanol?
It's butanol, but we got to be more specific than that if we want our marks, Tristan.
2-butanol.
Good. So yeah. It's 2-butanol, because the hydroxyl group is on position number 2. Please, it's not 3. You've got to start numbering from the end. You could also call this butanol. Both of them are accepted. Both will get you marks. So if I want to do an elimination, who can tell me what I should react this with? What materials should I react it with?
Sulfuric acid.
Good. Now please note, in this specific case, I've written out a plus, but I actually shouldn't. If I write plus H2SO4, that means that H2SO4 is actually something that we end up with as part of our products. In this specific reaction, we're going to remove the OH and one of these 2 H's. So we're going to end up producing an alkene and water. Sulfuric acid is not part of our reaction end products. So what we should in fact do here is move this to be under there. So this actually shows us that in this particular reaction, sulfuric acid acts, and you may view this as either being a catalyst, or I far prefer this definition, a dehydrating agent. A dehydrating agent because it is physically removing water. But you can put it in as part of your reaction conditions, and you can treat it as an inorganic reactant. But just when I write it here, I don't want to write plus H2SO4 because I don't want to put it on my products. It's going to look silly. What alkene am I going to form? So I'm going to ask everybody right now to write down the rest of this equation, and then I'm going to do the same. I'm going to pause now. I'm going to stop sharing, and I'm going to ask you to do it. I'm going to do it, and then we're going to compare in just a second. All right, go for it. Okay, please give me a thumbs up when you're done. Okay, well done. Good, good. Okay. Now you've got to remember in this case that you've got to apply Zaitsev's rule. So I only want you to draw for me the major product. If you want, you can draw both, but I want you to indicate very clearly for me which is the major product. We usually care more about the major product than the minor product. All right. I think that's a little bit of time. I'm not giving you too much. We've got enough. We've got to get through everything. So over here, if you look at this, what you'll see is we have two places that we could remove the hydrogen from. This carbon has got 3 hydrogens. This one's only got 2. So using what we said was Zaitsev's rule, we take from the poor, we take from the one that doesn't have any. So we're going to remove both of those 2, which means that the double bond is going to form between them over there, which is why the double bond forms there. Okay, I've lost a hydrogen. Sorry, apologies. I should have another hydrogen. Just something, it doesn't matter if these 2 hydrogens are above or below, or if one's above and one's below, as long as there is 1 hydrogen there and 1 hydrogen there. And then my water. Please get into good habits. If you're asked to draw structural formulae, you must make sure that you very clearly show the water and its bonds. So many people lose a mark because they write in H2O and it said structural formulae, which means you shouldn't have that. All right, can I quickly ask who got that correct? Thumbs up if you got it right. Fantastic. Okay, so some of you did get it. That's good. That makes me very happy. All right, let's do another one here. If I instead start off, actually, let's just do this here. If I start off here and let's make that a ClH. CH 3H H. Okay, so if I start with this, I want to do a little bit of name practicing. Can I ask quickly if anyone has any idea how we name this? You can interrupt me or you can type it out. Yes, Tristan, what's your answer?
Well, it's 3, so it's prop, and then it would be is that prop 1? No, it's chloropropane, right? Chloro 1 propane.
1 chloro.
There we go. 1 chloro.
2 methyl propane. So you had to realize that we had a branch off here. This was methyl. technically the C from chloro beat the M from methyl, and that is why we number them in this order. All right, thank you for assisting me there. Brilliant. Okay, so ladies and gentlemen, I would like to know in this particular reaction, so when we did the alcohol with sulfuric acid, we didn't put the sulfuric acid in as a starting material. Here, when we do a reaction with, for example, potassium hydroxide, and I tell you that it is concentrated, we do put it in as part of our starting materials because it is going to react and form part of our products. I'm going to pause right now. Can I ask you all, please, to write down for me what you get as the products here? Warning, there are 3 of them. Go for it. Oh, and remember, everything I want a structural formula, so show every single bond. Don't get lazy and don't get forgetful. Okay, please can I ask for a thumbs up when you're done? Okay, good. Good. I'm waiting for one more thumbs up and then I'm going to do it. Okay, yay, well done. All right, so I'm going to share this again. Okay, so we had our 1 chloro, 2 methyl propane reacted with concentrated potassium hydroxide. In this particular case, because the chlorine was our leaving group, okay, technically the terminology of leaving group isn't something we really teach in matric, but I find it so helpful to figure out what's happening. It's leaving. It has to go with the neighboring carbon's hydrogen. There is only one option, okay? If this leaves, the double bond has to form there. The methyl group stays where it is, so these 2 effectively get removed. Okay, so that is the product that you get. Also, we have our potassium chloride and our water, which comes from the water technically is the hydroxyl from the, well, technically hydroxide from the potassium hydroxide and the hydrogen there. Those 2 join together and that gives us our water. All right. Can I ask quickly who got that correct? Well done. Okay, so some of you are getting there. It does take a little bit of practice sometimes, which is why this is hopefully starting to remind you of what you did before. Last thing I want to quickly look at is the naming of this compound, because quite often they won't only ask you to draw the product, they'll ask you to name it. And if you can draw it perfectly but can't name it, you're in just as bad a position as if you couldn't draw it sometimes. So drawing this, we've got carbon number 1, 2, sorry, naming it. We've got carbon number 1, 2, 3. There's a methyl group on 2. Who would like to guess a name? Well, hopefully not guess. Who would like to tell me the name? Anyone? All right, so there's a 2. So it's 2-methyl. Yay, someone's going to tell me. 2-methyl prop 1-ene. Thank you, Gabby. Thank you, Rita. Gosh, you guys are all there. Just be careful with your naming. Between numbers and letters, you put in a dash, like that. Between numbers and numbers, you put in a comma. And between letters and letters, you put in nothing. So this is 2-methyl prop 1-ene. Okay, the ene is because of the double bond. Okay, fantastic. I think that most of you are beginning to get this idea here. Can I ask one interesting question? Who found that me suggesting a way to tell the difference between when you use sulfuric acid and when you use the base actually helped them. Has anyone ever got confused about the difference between the two? I don't know why. It's one of those things that I struggled with when I was at school, was that I'd often sit and go, oh, flip, it's one of the two. I know that it's either the sulfuric acid or the strong concentrated base, and then you take a 50-50 every time. Whereas now all that I do is I go, wait a second, if we've got an alcohol, alcohols use sulfuric acids and esters, so you use sulfuric acid. Then it's nice and easy. Please do remember though, that the same thing same reaction could happen if you had H3PO4, phosphoric acid, but it's also got to be strong. All right, and that's only for an alcohol. All right, ladies and gentlemen, I am ready to move on because we've only got an hour for our lesson today. I want to make sure that we get through everything. The next thing that I'd like to discuss with you is cracking. Probably going to make myself decidedly unpopular if teachers are watching this, but when it comes to cracking, I picture in my head that cracking is a giant long molecule and I have scissors and I can cut it wherever I want to. And it's almost with cracking, it's almost like letting toddlers free with 1 meter lengths of ribbon. If I gave a bunch of 20 toddlers a meter length of ribbon and a pair of scissors, you'd find the one kid who cut it once and then grew bored and wandered off to go and eat something. You'd have the kid who cut it 100 times, and you'd have so between all the kids cutting their ribbon with a pair of scissors, you would end up with a range of different lengths. Now, the same thing happens with cracking. So cracking is effectively, I'm going to just read this, so please write it down if you need it. I'm not writing it. It is a chemical process in which longer chain hydrocarbon molecules are broken down into simpler or more useful molecules. So the key words here are that it is a chemical process in which longer chain hydrocarbons, we don't crack other things, we don't need to worry about them. So if you remember, hydrocarbons are your alkanes, alkenes, alkynes, are broken down into either simpler, but the simpler are technically more useful. They're better starting materials, at least, molecules. So this is what happens when we get crude oil from under the ground. We can get a long molecule that maybe is C60H. Now let's make this an alkane. So remember, all alkanes have the rule CnH2n plus 2. So let's make this C60H122. So I'm dealing with something huge here. I'm not dealing with something small. When we break this down, we're going to do so under both high pressure and or high temperature. Now, I know that if you learn this, you'll find that there's catalytic cracking and there are all sorts of different kinds. That's not usually what's examined. What's usually examined is that you get the full idea that when you break it down into smaller pieces, you get a range of different products. I never expect you to know off by heart what we're going to get from C60. In fact, I'm making this up right now, okay? I don't know the answer, but I do know one thing. I do know that however many pieces I break it up into, I must, non-negotiable, have 60 carbons and 122 hydrogens, non-negotiable. Also, as a rule, if I start with an alkane, in the process of breaking one of these bonds, I am going to end up, so R in chemistry just means and everything else. Okay, so it's an alkane group. If I do this, I'm going to end up technically with two sides afterwards, which would both want a hydrogen, but they can't both have a hydrogen. So what typically happens is that the one side will get the hydrogen, okay? So one side will get a hydrogen, but that hydrogen has to come from somewhere. So it comes from here, and the other side ends up forming a double bond. Okay, so what we typically find is if we start with an alkane, we must end up with at least one alkene, all right? So your product will end up as a mixture from an alkane of both alkanes and alkenes. Okay, because your hydrogens aren't necessarily going to work in exactly the right balance. So sometimes you're gonna end up with an issue. So what I find here when it comes to cracking is all I care about is that my products have fewer carbons than my starting material. I can't end up with more carbons. I'm snipping things, I'm breaking them. So if I were to do an example for you here and tell you that 2 of the products are C12H, now I'm going to be careful here, this should be 24, 26. If I told you that 2 of my products were those, and there was one other product, what would this other product have a formula of? Let's start with the molecular formula. We can figure out what it might look like. Well, maybe not. It's 22 carbons, not, well, 20 something carbons, not drawing it. So I'm going to count carbons and hydrogens. My carbons here, I've got a total of 24, and my number of hydrogens, it's been a long day, is 56. That means that the number of carbons and hydrogens left, I started with 60, I used 24, I've still got 36 of them left. And here my hydrogens, I started with 122, I used 56 of them, I've still got 66 left. So I know that the product that I get, if I haven't messed up on my maths, is C. That looks a little bit wrong. What did I do wrong? Someone can really tell me. Isn't it 52? Thank you. All right, wait, where's the 52? Oh, here. Okay, yes. I knew I'd ended up with too few because I didn't have close to twice as many, which is what you should do. So here, I did that on my calculator and it came out funny. That is 52. 26 times 2 is 52. So 122 minus 52. Thank you for people who can do maths at this late hour. I ended up with 70 there. And if you look at that, you can actually see that this probably has a triple.
Isn't it 78, ma'am?
Is my maths that bad? 122 minus 52.
Isn't it 26 times 3?
26. Okay, just give me a second. Bad maths day. So here we've got 60 from there, and we've got 2 lots of 12 for my carbons. Okay, so that'll be minus 24. This is definitely 36. Okay, so basically what I'm doing, I better show you my maths, is 60 minus 2 times 12 must equal the number of carbons. So 60 minus 2 times 12 does give me 36 carbons. Let me go slowly. Then for my hydrogens, 122 minus 2 times 26. And this is 26 because this is 12 times 2 plus 2, which is correct. Okay, that I did right. So here, if I have 122 minus 2 times 26, I should do smaller maths in future, I still get 70. So this is, there we go. That little bit there got a bit confusing, so I'll make it straight again. So this is C36H70. If you look at that, okay, don't worry. I don't mind if you guys make mistakes as long as you correct mine. So if you make mistakes, that's okay. If I make mistakes and they're still in this video, people do them in exams and then I'm in trouble. So if we look at this, 36 times 2 is 72. And we've actually got here CnH2n minus 2, which means that we could actually predict that this would not just be an alkane, it would be an alkyne. But you can see how we can predict what it is based on what everything else was. Okay, so the key idea that I like to teach my students when it comes to cracking is it's literally us cutting. You're not supposed to memorize what products you get, but you should have a general rule that says whatever products you get will have fewer than 60 carbons here, because we started with 60, so you must have fewer carbons, and that you'll end up with the sum of carbons totaling the original and the sum of hydrogens totaling the original. Once you've worked out the molecular formula, you can use the rules that your alkanes are CnH2n plus 2, your alkenes are CnH2n, and your alkynes are CnH2n minus 2 to try and figure out what you've got. All right, there aren't even rules. Like at the end of the day, I might know that what I get is C4H8, but I won't know whether the double bond, which position it's in, which is why in the exam they'll award you the marks whether you put your double bond between carbon 1 and 2 or between carbon 2 and 3. So you can't always tell the difference between the isomers, but you could realistically say that there's a chance that both isomers did exist because of how the snipping happened. All right, can I quickly clear this? And then I'm going to do one example with you, a very quick one, before we move on to our esters. All right, hopefully we'll get to polymerization, crossing fingers. All right, so if I started with C8H, I've got to think this through, 1618, okay, which is octane. And I did my cracking, so I had my high temperature and high pressure. I'm not going to write them in right now. And one of my products was C4H8. Can I please ask everybody to work out what this is and then to try and name it? All right, I'm going to pause just quickly so that you can do both of those. Good luck. Go for it. All right, it shouldn't take you very long. All right, who's already done it? Thumbs up if you've done it. Well done. Fantastic. Good. Fantastic. And a whole bunch of you have already got to the answer. All right, so I'm going to quickly resume sharing. I counted my number of carbons and I figured out that I needed to get to 8. There it is. I counted my hydrogens and I figured what I needed to get to, and that told me the answer. All right, so since it had CnH2n plus 2, I figured it was an alkane. If it has 4 carbons, it can only be butane. Okay, can I just quickly ask, who found that this method of thinking of cracking has helped them? I don't know why, but I find that cracking is one of those ideas that a lot of you just don't get. I don't know if it's that maybe your teacher showed you one example and then you really struggled to figure out how it applied to other examples. But I find that if you use this as a rule, it really does make it a little bit easier to just understand that there isn't this great expectation that you're supposed to remember things. Because I think that's often what happens to you, is in an exam you go, nobody taught me this. And then they're big eyes and you kind of go, I've never done this one with this thing and I don't know how. Whereas if you just think of it as little scissors cutting and that you're not expected to memorize what they are, you treat it with way less pressure and you usually do a lot better on it. All right, so we move onwards. What we're going to be looking at now is esterification. I find that a lot of people are really good at esterification because it's one of those things that you would have done at least your practical normally on. This year, I don't know if everyone's done their practical, but you'd normally do a practical on esterification, so you've at least had some experience. Our rule with esterification is that you have an alcohol plus a carboxylic acid in the presence of H2SO4 under reflux, which I show as the symbol triangle showing heat, we will end up producing an ester and water. Please, when you draw out your water, you must draw it out like that. Don't get caught out. Now, you do not need to know the full mechanism of esters, but you do need to know that when you draw them, the hydroxyl group of your alcohol must face the carboxyl group of your carboxylic acid. So if I started over here and I used an alcohol, I don't know why I'm starting there, let's just quickly go. If I used an alcohol here, I'm going to use methanol. 1 carbon makes it methanol. And I'm going to react it with the carboxylic acid of, let's do ethanoic acid, vinegar. When I react these two together, what happens is that we remove a water. Now, technically, the water comes there. It is actually the OH from the carboxylic acid that leaves, but nobody really minds if you draw your box in the wrong place. You'll still get the right product. So what's going to happen is this oxygen then joins directly on to that carbon. So you can pretty much imagine, I sometimes when I do it, take my fingers and cover up all of this. So my fingers would be sitting across here so that I can't see it. And then I redraw it, missing the bits that I don't want to be there. So when I draw it, I'll draw this bit first. Okay, so I draw my CH3, I draw my O, then my O joins straight onto, can't see all of this, not here, straight onto that C, double bond O, CH3. The way that we name, these, I'm going to teach you bad lessons for a lot of these things, but it works. There is no specific name and mine works. So this over here, remember, was ethanoic acid. I always name mine, and you never write this down because your teacher will think you're crazy, but it is alcohol aisle, carboxylic acid, Ca is carboxylic acid, O8. So my alcohol was methanol, so this becomes methyl. My carboxylic acid was ethanoic acid, so it becomes ethanoate. And I find that that's a very easy way to remember it. Please don't forget, I know I've already drawn your water, I'll remove it now, but there, take away the old water. That is your product. All right, so that is how we do esterification. You need to know certain things about esters. You need to know that they smell nice. Nice is very much an opinion. I find that some esters give me a very big headache, but they smell nice. They're the fundamental chemical that we use in perfumes, in fragrances, and in flavorants. I just want to point out something with flavorants. Quite often people will go and say fragrances and flavorants like they're all double up. It's true that for certain things like vanilla essence, it tastes nice because it smells nice. But if you've ever eaten vanilla essence straight, it is revolting. And if you've ever caught a mouthful of perfume, it is also revolting. So please do not think that they necessarily taste nice. They smell nice, and in very, very low doses, they can also taste nice. If you have them concentrated, they're revolting. Okay, so ladies and gentlemen, I'm going to presume that most of you are very competent on esterification. So what I'm going to do with you, instead of just doing the going forwards and the naming, I'm going to do one with you where we go backwards, because the backwards is a little bit trickier. So I'm going to start by telling you what the ester is, and I'm going to ask you from that to figure out what its alcohol was, what its carboxylic acid was, or the ones that we use to make it, and then to write out the full equation for it. Now, to explain to you how to do this, I find that the easiest way to figure out what the name of an ester is to draw a dividing line through the oxygen that merged them. Okay, this oxygen merged them. I draw a dividing line through it. I then look at my two sides. The one that has a C double bond O, that is where my carboxylic acid came in. So I count how many carbons there are. There are 2. That means that I know that my carboxylic acid had 2 carbons, which makes it ethanoic acid. Easy. Obviously, you've got to still be able to draw ethanoic acid, but that's the easy bit. I go to the other side, and I know that this must be the side that my alcohol came from. It's only got 1 carbon, which means I know it came from methanol. All right, so I find that this trick is one where if you don't know it, it can be very difficult, but most of you, I think, have already learned that. All right, quickly take a screenshot if you need to, and then I'm going to draw the product, and you're going to tell me how we make it. All right, okay, so let's quickly get going. Can I ask, can anyone here looking at this quickly tell me what its name is?
Ma'am, is it propylmethanoate?
Okay, perfect. We've got 3. It's okay, so we draw 3 here. This side came from our alcohol, so it's 3. So it is propyl. Well done. And on this side, there's only 1 carbon, so that makes it methanoate. Okay, can I ask everybody to quickly draw the carboxylic acid and the alcohol that made it put their functional groups towards each other, so it's easy for you to take out the water and to see, well, I guess you can already see what your product is. I'm going to quickly pause it while I do all of this, and then I'm going to show you at the end. But I'm hoping that you all will have a picture that says alcohol with a picture of the correct alcohol plus carboxylic acid gives me methyl propanoate plus water. Go for it. By the way, in an exam, you do not need to show the box with the H2O coming out. I just find it was something that I learned when I was in school, and it makes it a lot easier to draw it if you struggle with it. All right, who's already done with that? Okay, well done. Fantastic. It seems some of you are working faster than I am. Okay. All right, let's go through this. So that is what I get over there. So let's just quickly go through the names of the alcohol and the carboxylic acid because they're likely to ask us. So this is propanol. Technically, we can be more specific than that. It is 1-propanol. The hydroxyl group is on carbon 1. And I'd recommend when you're writing down an alcohol, just out of security, unless it's methanol where there's only one position or ethanol where there's only one position where it could be, as a rule, write down the position of the hydroxyl group. Over here, we have methanoic acid. Acid. This is propyl methanoate, and then please don't forget to draw in your water. Okay, please also don't forget that we use sulfuric acid. The sulfuric acid is described as either being a catalyst. That is the first answer I always want you to write down, but it is also technically a dehydrating agent again, but that's usually not the first option on the memo, so it's safer to go with it acts as a catalyst. Speeds up the reaction that otherwise might not happen quite so quickly. All right, one thing that I'd just like to quickly point out here while we're on this discussion is the name of, okay, now the name of the ester should, this is where we get very tricky. Technically, it should be one word, but it shouldn't. So I find what I do, because I never actually know exactly whether it should or shouldn't be. I like writing it as two separate words. I do. But what I do, just in case someone's going to get on my case about it, is I usually, you know, like when they teach you to write, you learn to put a finger space between two words. I make sure that the space between the two is a little bit less than a gap. So it's a gap that I can see that I'm comfortable with as being a gap. But it's also so close that, I mean, there's a gap too. You're not going to get technical and take away my mark because of the space. All right, so esters are the one writing out of names where you can have a little bit of a space between propyl methanoate without it being an issue. But I don't recommend you make it too big just in case someone's decided this is the year to clamp down and it isn't correct. All right, okay. Is everybody happy with that? I've always taken it as being two words, and I'm quite happy to continue to, but it's just something to be aware of, that if you make it like hugely separated and somebody does decide that that is now something that you can penalize on for whatever reason, I don't want you to be the victim of that. Okay, so I don't think you should get penalized, but just in case. All right, can I quickly pause before we do polymerization? Does everybody understand everything that I've done, and is everybody good with what I've done here? Okay, perfect. I'm going to try in the next 9 minutes to cover how polymerization works. Okay, so polymerization in an exam is usually worth no more than 4 marks. It's not something that many teachers stress about too much, so it's one of those things that often kind of gets left off. I like polymerization with an S, but I'm going to go with polymerization. There are 2 kinds of polymerization that you get. You get a polymerization, which is called addition polymerization, and you get one that is called condensation. Okay, so I'm going to pause before I lose myself, and I'm going to go back and explain to you what polymerization is. Polymerization is the process of linking or joining. I'm going to go with joining, isn't on my notes. Joining monomers together. Monomers are individual smaller particles to form a longer polymer chain. It's not the real definition, but it's close enough. So monomers are our small repeating units. Just like I have a mental picture for when I view cracking as being a long chain being snipped at with scissors, polymerization for me, when my son was little, they used to make these beads, and I've left off the bead bit. They used to make these like weird beads that had a bit at one end and then a hole at the other. And you could stick this end of one bead into this hole in the other, and you could link them together and make a chain. You could also view it, I guess, a little bit like taking beads and threading them together to make a necklace, but then you'd have the string as well, and we don't really have anything that represents the string. So I kind of view it as being interlocking beads that link one into the next, into the next, into the next, and then they form a long repeating unit. Now, that is what polymerization is. Monomers are the small repeating units. Polymers are the long chains formed from the small repeating units, and there are two different ways that we join them. Please note you cannot join any two monomers using either addition or condensation. What type of molecules you're joining will determine what kind you get. So in addition reactions, we must do an addition reaction, which means we must join together alkenes to form an alkane. So one of the examples here is that if I start with ethene, I can join a whole bunch of ethene molecules together. Now, please, I'm giving you a very simplified version of this. If your teachers taught you this properly, which they don't really have to do because we don't always examine it, there are 3 steps to addition reactions. Addition, okay, sorry, not addition, there are 3 steps: initiation, propagation, and termination. So there's a whole process where we have to create a free radical, get the free radical to perform a, I think it's a nuclear, perform an attack, break the bond. There's a whole process that we got to go through. We don't usually examine you on this, so I'm teaching you the shortcut method. The shortcut method says I start with ethene. Here's the theory. I want to form a bond this way and a bond this way. In order to do that, I must break one of these bonds. So my rule when I do this with my students, to show you what your polymer gets, so this will be polyethene, also known as polythene, we will have the 2 carbons that you started with, but only a single bond between them. The 2 hydrogens here get swung around up. So this guy gets swung up, this guy gets swung down, this one gets swung up here, this one gets moved down, and then we join on here. But the point is, it isn't just one monomer joining together. We've got an infinite number of them. So if I've got 20 of these, I'll have 20 of these joined together in a chain. So what we usually can do, instead of writing 20, which I actually started to do, is we can write n of these will join together to form n of those. Please note, this usually is shown with brackets. That was a very bad bracket. So it can be square or rounded brackets to show it. Okay, so that over there shows the process. There are only a limited number of these that you can be tested on because there are only a limited number of the alkenes that you can actually name. So ethene is the first. The second that I can show you looks, yeah, okay, so I'm just quickly going to remove all of my unnecessary drawing here so that it looks correct. Sorry, just going back to the first diagram there, so I can put in n of these will give me that. Now, if I started with the molecule instead, which had chlorine there, and all of these are hydrogen, okay, so that means my monomer is 1-chloro-, ethane, then the polymer that I get pretty much has a chlorine on every second carbon. I don't know why I'm writing and talking at the same time. Messing it up here. And this is known as PVC, polyvinyl chloride. You don't need to be able to spell it, but it's polyvinyl chloride. Okay, polyethylene, polythene, they got different names, same thing. Polyethylene, all good. Okay, go with whatever your teachers told you, but technically they're all good. All of these are plastic. Our most common kind of plastic, like plastic bags, Coke bottle plastic, and cling wrap. All right. Okay. So because it's plastic, it's got many different names. It's very popular. PVC is the thing that we use for our piping. And then the last one here, I'm just going to do it in a different color so you don't get it confused, is that if I do propane. Propene has 3 carbons, but I'm going to do the last one facing up. The reason that I'm doing it facing up is it's easier to imagine what we'd draw it as a polymer if we start off with the monomers looking a little bit weird. So here, if I have 2 carbons and this has a CH3 group, obviously you draw it out in full if you can, but that over there is going to be, this was propene, and this is polypropene. Okay, so those are the 3 addition reaction or addition polymerizations that you're likely to need to know. You can always identify that something is a polymer by the cunning use of this little N. Just says that it's going to keep repeating and it's a long chain with who knows how many things in it. Okay, so our plastic that we use, plastic, PVC, polypropylene, all of them form long chains and therefore are very useful as textiles or as materials to work with. Condensation polymerization gets a little bit trickier, but to make it really easy for you to understand, we're effectively going to be forming a condensation bond, which is an ester bond. So typically what we will do here is we will have a substance, I draw the middle bit as a triangle, doesn't really matter, and on one end it'll have a carboxyl group, and on the other end it could either have another carboxyl group, and then it will react and bond with something that behaves like an alcohol, so it has an OH here and an OH there, or we could have something that instead has a C double bond O, OH on this end and has a C, OH on that end. But the point that we're going to make is we're going to join these together by joining this end of one molecule with this end of another molecule, and we effectively just join them with esters. The way that you will see that you have got a condensation polymer is that typically you will end up with something which has O and then whatever it is, a repeating unit, and then it will go on and it'll often have an OC double bond O and then something else, and then you'll see that you've got lots of these kind of ester linkages, and most importantly, when we finish the whole thing up here, sorry, I shouldn't end on an O, I started on an O, it will have an N. We usually do not examine you a huge amount on condensation polymers other than to bring something up. So I'm just going to quickly give you an idea of what you could look at as being condensation polymer. I'm just going to clear my board in a second. But basically, you'd look at it, you'd see that it has an N, which makes it a polymer, but it doesn't look like any one of those. Or you can see that it's actually got this ester linkage. Then you know that it's condensation polymer. We usually don't even practice naming them particularly. All right, so I'm going to quickly just clear everything here. Then I'm going to show you, for example, in those two questions, they often have a number of things. So if I were to have an example, I'm just quickly picking on one here, and I were to have this as my monomer, okay, just that. Doesn't even have to be like that. I can join it with another one here. OHCH, yeah, that's correct, C double bond O, OH, and you can see here that I could take out water there, but you could see that the same thing is going to happen again here with something else, and is going to happen again here with something else. So what you can figure out is we're going to have from here to here repeatedly. And that would then be our repeating unit. But we usually, as I've said, don't specifically focus on examining this, so please don't stress too much. All right. Okay. Ladies and gentlemen, I hope that this has made a little bit more sense to you with regards to organic reactions. Please, can I recommend that you actually go and practice a huge number of question 4s from your chemistry paper so that you can check that you do understand what you are supposed to be able to do. All right. Have a lovely evening.